So good morning, everyone. Today we have the pleasure to welcome Dr. Giacomo Corti with us. He's director of research at the National Research Council of Italy in Florence. And today he's going to talk about the architecture and evolution of the main Ethiopian rift, which is the most northern segment of the East African rift, and he's going to tell us about what controls this evolution and talking about tectonic inheritance and plate kinematics. So Giacomo, the floor is yours.
Thank you very much. Can you see the screen? Can you see the presentation properly? Is it okay? So thank you very much, first of all, for the invitation and for this very interesting initiative, which is very useful for people like me who likes to watch recorded videos or presentation and to gather more information on different sectors and of the East African rift and or rifting in general. Today I will introduce some of our work on the main Ethiopian rift, focusing on the evolution of the architectural rifting and the control exerted by parameters such as tectonic inheritance and rift kinematics on these aspects of rifting. And we are, happy to work in Ethiopia because it's a special place to work on continental rifting because, first of all, it is a magmatic rift that records all the different stages of at least many different stages of rifting from the initial phases to more advanced rifting and incipient oceanic spreading in the Afar depression. And so we can see many different stages of the evolution of the process in different parts of Ethiopia. And also these processes are ongoing, so they are active as testified by the several volcanoes, volcanic eruptions and earthquakes related to the process. So we can really capture, monitor, analyze real time some of these volcanic and tectonic events. So Ethiopia is really a very special place to analyze all the different processes. And we have done this in recent year by using a methodology which integrates different approaches. And today I will show you examples of this integration. Of course, we are structural geologists, so we like to work in the field. We like to go in the field. We need also to analyze rifting from satellite images or digital elevation models. So we need a remote analysis before going in the field. But also very important to us is another methodology, which we use quite a lot, is an experimental technique, which is analog modeling. So we reproduce these very large tectonic processes in the laboratory by using models which are very small and formed very rapidly in a few minutes or hours. So very rapidly if compared to the slow geological processes. And I will show you some examples of this very simple but normally very useful analog models. So I will show you examples of this. Where we are at the northernmost in the northernmost sector of the East African rift, where the continental rift valley of East Africa links to the oceanic domains of the Red Sea and Gulf of Aden. So we have the interaction of three plates here. We have Africa, Somalia, and Arabia, and the tribal junction between this among these three plates is located here in central Afar. And we are mostly interested in what happens south of this triple junction in a region which is called the main Ethiopian Rift, here south of the Afar Depression, which is here. And in this specific location, like the almost all the East African Rift, the formation is controlled by the motion between the two large plates of Africa and Somalia, whereas south of the Turkana Depression, there are minor intervening microplates which somehow complicates the plate kinematic setting of the rifting process in East Africa. Rifting is very slow in these areas, occurs at rates of 4 to 6 millimeters per year, whereas the motion of Arabia with respect to Nubia and Somalia is faster. It occurs at rates which are 1.5 to 2 centimeters per year. And we will see, which is very important, is that the motion between the plates occurs in a roughly east-west direction. You see here the arrow, which indicates the motion of Somalia with respect to a fixed African plates as derived by recent GPS analysis. Rifting in this area, as in many parts of the East African Rift, has been preceded by some significant related processes. On the one side, we have the rifting, as in many parts of East Africa, is superimposed on a very anomalous topography. There is a very large region characterized by an anomalous topography in which more or less involves the southern and the eastern part of the African continent, the so-called African superswell, which has uplifted probably since the Oligocene, probably in a complex way, or at least in a way that we don't know exactly, or it's somehow debated. And this anomalous topography is in Ethiopia and the Horn of Africa in general, also accompanied by a voluminous phase of volcanic activity with eruption of float basalts, which have occurred well before rifting began in this area, with eruption of basalt started in South Ethiopia at 40 to 45 million years, and more recently in the northern part of Ethiopia, probably at around 30 million years. But we have eruption with this very large volcanic phase, with eruption of basalts up to 1.5 to 2 kilometers in thickness. So these two events are related to very limited extension, so very limited and localized deformation has affected East Africa during this initial stage, and I will show you later when this began in Ethiopia. So this, I will not enter into the details of this, but this tells us that there is a significant contribution of an upwelling mantle, mantle dynamics in rifting in this area. So what we call active rifting, so rifting dominated by upwelling of hot mantle material from depth. So these are somehow phases which are related to very limited deformation in this area, and deformation started later with respect to this event and were related, as I told you at the beginning, by roughly east-west motion between Nubia and Somalia at the rates that I indicated before, something like 4 to 5 millimeter per year. And the formation in this area was localized and significantly controlled by the presence in this area of a pre-existing weakness zone, a proterozoic suture separating the lithosphere beneath the Ethiopian and the Somalian plateau. So we had these two strong blocks beneath the Somalian and Ethiopian plateaus and a weak zone in between. So the formation strongly localized in this weak zone, which is something typical for rifting in East Africa, but in general, and it is something that was recognized since a long time, like here in the classic paper by Beresford and Rosenthal, which associated this to the rupture of the bricks buildings, where the tensile fractures, they tend to avoid the strong bricks and to localize in the mortar in between them. So normally the fractures tend to localize in the weakest part of a wall or a lithosphere in the case of continental rifting. So we have a strong localization of the formation in this area, and the initial phases of rifting were characterized by the heterogeneous in time activation of large boundary faults in different sectors of the Rift Valley. I think a lot of work still has to be done on these initial phases of rifting, on the timing of the activation of the large boundary faults in the different parts of the main Ethiopian rift. But what we know now is that we had an early activation of faulting in the southern part of the rift. Here, something in between 17, probably between 17 to 20 million years. Then we have activation based on geological data. We know that the activation of the large boundary faults in the north occurred likely in between 10 to 12 million years. And then we have a later activation of the large boundary faults in the central part of the Mid-Ethiopian rift, where the activation of this large structure occurred probably in between 7 to 8 million years, based on both geological data and apartheid fission track data. So we have a time heterogeneous activation in time of these large boundary faults in different parts of the rift. Here you see some beautiful pictures of these large boundary faults that I will show you. Some of them are still active and still accommodate a lot of deformation in different areas. We have beautiful landscapes associated with these large boundary faults. We have beautiful outcrop of fault plains where structural geologists can really be happy to investigate all the small scale features associated with the small scale characteristics of these normal faults. And as you can see from the top view or the plan view map of these large boundary faults, there are significant variation in the trend of these large boundary faults, which pass from roughly north-south trend in the south to more northeast-southwest trend in the north. So we have a significant along axis variation of the trend of these large boundary faults. And I will show you later that this is very important, because of course you have to consider that the vector of motion Nubia and Somalia is constant all along the main Ethiopian rift, because the pole of rotation between the plates is far from here, is south of this area, but very far. So the vector is more or less constant all along the main Ethiopian rift. So the different orientation of the rift, which is controlled by the geometry of this pre-existing weakness, creates conditions of orthogonal rifting in the south and conditions of oblique rifting in the north, because the trend of the rift in the north is oblique to the vector of motion between the two major plates. And I will show you later that this is very important for the architecture and the evolution of rifting in the area. If we if we analyze the along axis variation in the characteristics of the different sectors composing the Mediterranean rift, what we see is that we have a transition from sectors where the rifting is significantly asymmetric, like here, for instance, or in this southern part here, and other sectors where instead the rifting is more symmetric. So we have, as in other parts of the East African rift, we have alternating portion of asymmetric and symmetric rifting. And this occurs in many different parts of the Mediterranean rift. So we have alternation of symmetric and asymmetric portions. And this is again, most probably related to the pre-existing structure of the lithosphere in this area. And in particular, we have a significant variation from a more homogeneous and stronger lithospheric block in the Somalian part, beneath the Somalian plateau, to a more heterogeneous and probably weaker lithosphere beneath the Ethiopian plateau, so to the west of the rift. And in particular, we also have the occurrence of two transversal weaknesses here in the Somalian plateau, which are marked by this whitish pattern here, the Yerer Tuluel and the Goba Bonga transversal lineament. And where we have that this pre-existing transversal weaknesses, they cut, let's say, the rift at a high angle here and here. We have a preferential development of asymmetric rift, asymmetric basis, with the main boundary force, which is located on the opposite side, so on the stronger, on the side where the stronger lithosphere is localized. So we have these alternating portions of the rift, which are controlled by the different nature of the lithosphere at both sides of the rift. And I was telling you before about the analog modeling approach. In this case, we have run very simple analog models to analyze the influence of these transversal weaknesses on the development of these asymmetric portions of the rift. Here, I just show you very quickly this kind of modeling which I use to investigate these processes. This modeling, as I said before, they try to condensate the complex geological system in experiments which are dimension are very small. You see here, this bar is 3 centimeters. So the models are normally something like 15 centimeters wide and let's say 10 to 15 centimeters long. So they are very small with thickness which is normally of a few centimeters. They use very simple materials like sand or silicon, as normally done in analog modeling, to reproduce the complex stratigraphy and the vertical stratification of the crust or the lithosphere. So they, of course, have to simplify the complex geological systems. And in this case, we reproduce, as I said, the occurrence of a localized deformation here in a rift valley, which is orthogonal to the stretching vector between the two moving plates, with the occurrence of a transversal weaknesses, which give rise to this kind of T-shaped weak zone in an otherwise strong model. Normally, the scale of this model you see here is that 1 centimeter is something like 15 to 20 kilometers in nature. But of course, these models, as I said, they are simplified version of the natural system, but they are somehow realistic replica of a certain geological system. So we can use this experiment to test the importance of different parameters on the evolution of a rift zone or another geological process. I will show you later some movies of this kind of experiments, and then here I'll show you some top views here. This is a photo of a model Rift Valley with large boundary faults, which are this structure here. This is the digital elevation model, which shows here in this blue pattern the more depressed regions of the model. So you have a subsiding reef depression here, which is marked, as you see in this left zone, by the absence of the large boundary faults on one side in the area which is characterized by the transversal weakness. And you see that the transition from a symmetric rift zone here, where the transversal weakness is absent, to a strongly asymmetric rift where the transversal structure is instead present. So we have this alternation of symmetric and asymmetric portions, which are related to the transition from a normal lithosphere to a lithosphere which is characterized by this transversal weakness. So something that can be somehow similar to what we see in Ethiopian nature. So we can somehow state that these transversal weaknesses can somehow control the alternation of symmetric versus more asymmetric portions of the reef. Sorry. So as I said, we have a transition going back to the architecture and the timing of development of these large boundary faults. We have a transition from the southern part of the rift, where the large boundary faults probably started to form at around 17 to 20 million years. Their trend is north-south, to a different trend moving northwards and a different timing of activation. The other important point is that in the southern part of the rift, these large boundary faults still accommodate a large part of the formation. GPS data confirm this, suggests that a lot of the formation is still accommodated at the rift margins in the southern part. Also, we have geological indication that more or less the same thing occurs here in the central part of the Ethiopian rift. Whereas in the northern part, we have something different, because we have geological data suggesting that these faults, which started at around 12 to 10 million years ago, they are now currently not active. So they have been deactivated. And for instance, GPS data suggests that a lot of the formation in this northern portion of the rift is accommodated at the rift axis. With this is somehow a simplistic view of the process, but probably, yeah, more than 50% of the formation, probably something up to 70 or maybe 80% of the formation is accommodated at the rift axis in this part of the rift, which is characterized by another system of normal faults, different from the boundary faults. And in fact, this second system of faults is mostly localized at the rift axis, which have been active since more or less 2 million years and accommodate the largest part of the formation in this region. So we have a different set of faults with respect to the large boundary faults, which accommodate or cut the rift floor, deform the rift floor in the northern part of the Mediterranean. And if you go in the field, you clearly see that these axial faults are very different from the large boundary faults. They are normally shorter and they have a more limited vertical offset. So they are normally smaller with respect to the large boundary faults. So they have different characteristics with respect to the large boundary faults. They are typically form clusters of echelon clusters of dense small faults at the rift axis, and they have a kind of different orientation with respect to the large boundary faults. You see here the boundary of the rift; they are northeast, southwest in this region, and these axial faults are instead more northeast, southwest. So we have these two different system of faults which have different timing and also different orientation. And this can be clearly see if we analyze statistically the faults in the different parts of the rift, of the Ethiopian rift. And in the northern part, as said, we have two different fault systems activated two different timing. So we have a two-phase evolution of rifting in this area. First, the large boundary faults, and then a migration of the formation at the rift axis with the activation of the axial faults in the last 2 million years. Whereas in the south, we have a single major rift system of faults, the large boundary faults, and we have almost absent axial faults. So we still have the largest part of the formation accommodated at the rift margin. So we have a clear long axis transition from two-phase rifting to a single-phase rifting in the southern part of the rift. And this is also associated to a transition from limited or almost absent magmatic and volcanic activity in the southern part of the rift here to a more abundant quaternary volcanic activity and magmatic activity with surface volcano, but also I will show you significant magma intrusion at depth. A quaternary volcanic activity which is mostly localized at the rift axis. And we have beautiful examples. Here's a beautiful satellite image of the Bosetti volcano in the northern part of the mid-Ethiopian rift with a typical alignment of volcanic bands along the north-northeast, south-southwest oriented axial faults. And again, these volcanoes, which are represented by silicic central volcanoes like Fantale here at the top, but also beautiful Mars and a lot of different volcanic bands in different parts of the central and northern main Ethiopian rift, and beautiful landscapes created by this volcanic activity. And this is an example of a very recent scoria cone, basaltic scoria cone close to Fantale. And this is also associated to significant geophysical evidence for important voluminous magma intrusion into the whole 70 kilometers of the continental lithosphere in the northern part of the main Ethiopian rift. And again, we have significant evidences for a localized magma intrusion in the axial portion of the rift in the northern part of the main Ethiopian rift. So we have a clear association of axial faults, surface alignment of volcanic vents at surface, and magma intrusion at depth. And also we have a significant geophysical evidence for an increase in magma intrusion passing from the southern part to the northern part. This is associated with also petrological evidences for a transition from less evolved magma plumbing system in the central part of the Ethiopian rift, where we have magma storage in the mid to upper crust with development of magma chambers and for instance, the development of large pallitic calderas in these sectors of the rift. Whereas in the northern part, we have a more evolved magmatic systems with almost no storage of magma in the mid to upper crust. We have instead fissural basalts fed by dikes directly from the lower crust. So we have a more evolved magma system with easier transfer of magma from lower crustal depths up to the surface. So to summarize, we have a transition from marginal deformation and almost absent volcanic or magmatic activity in the south to axial tectonomagmatic activity with abandonment of marginal deformation in the northern Ethiopian rift, which is associated to well-developed axial faults and rapid magma ascent and eruption from lower crustal depth to the surface. And of course, an increase in volcanic activity moving from the south to the north. And these along axis transition have been typically interpreted since the mid-90s by Cindy Ebinger and colleagues. This along axis variation have been interpreted as reflecting a transition from initial rifting in the southern part of the Lithosphere rift, with deformation localized at the large boundary escarpments, to more advanced rifting, to mature rifting in the northern part of the Lithosphere rift, where deformation and the volcanotectonic activity has migrated from the margins to the axial parts of the rift. And this evolution has been confirmed by several different studies, including our analog modeling. And I will show you some other examples of this kind of modeling. In this case, I will show you an oblique rifting model, but the same evolutional cues for orthogonal model. Again, we have a complex stratification of the model, which is supposed to reproduce the complex stratification of the continental lithosphere, of course, in a simplified way. We have a central weak zone, as in nature, which localizes the deformation. We have, again, materials such as sand or plasticine silicon mixture to reproduce the different ductile and the brittle layers of the continental lithosphere. We have, again, a scale which is 1 centimeter in the model represents 15 kilometers in nature. We have a scaling of the forces and the velocities imposed to the models in order to have a model which is a realistic replica of the complex geological system. So that, as I said, we can investigate the influence of different parameters on the evolution of our complex geological system. In this case, the model is intended to reproduce the evolution of the continental rift, and I will show you a top view, different top view photos of the model, which reproduce the evolution of a rift valley like the one characterizing the Ethiopia. So you see, this is a top view of one of these models. You see that the model will start to extend laterally. So these two mobile wall which confine the model, which is this one, we start moving one with respect to the other. We start moving laterally, and the formation will be localized in the central part here. And you will see the two-stage evolution that I was telling you before. You see at the beginning, this is a rather complex arrangement of large boundary faults, which are this here and this here. You see the complex architecture of faults, which are typically characterized by an echelon arrangement of these faults, because the kinematics is not orthogonal in this case, but it is oblique rifting. So we have a component of transcurrent motion. So this gives rise to this complex pattern of faulting with an echelon faults and sigmoidal faults. But anyway, what it is important to note now is that we have this marginal deformation here, marginal deformation here with large boundary faults, with antithetic faults defining a sort of marginal grabens, but we have no deformation in the axial portion of the model. So we only have deformation at the border faults and at the rift margins. This happens during the initial stages of model deformation, but if we go on with progressive deformation, we see that things at some point start to change, and you see that there is some deformation starting to affect the central portions of the model. And in this case, you see that we have faults at the rift axis, faults which have a trend, you see, different from the boundary faults. They are orthogonal now to extension. And you see that the picture of the formation has changed quite dramatically. Yeah, development of axial fault and a decrease in the activity of the border faults. So even if you analyze the model in cross-section, and we can do that freezing the model and cutting progressive cross-sections, you see that this is the undeformed model. This is the photo of the cross-section and the interpretation of the cross-section. And you have an initial stage where you can clearly see here boundary faults in cross-section and marginal grabens with antithetic faults. So we have a couple of marginal grabens here. We have in gray sediment accumulation, and we only have developing internal faults, but no significant deformation visible at surface in this phase. Whereas if we increase deformation, you see that things change. We have the development of a sort of another graben structure at the rift axis. So we have internal faults in the central graben and a decrease in the activity of the boundary faults and the marginal grabens. So we have a two-stage evolution of our models. We can analyze in any detail this, but the most important message from this model is that we have a first stage of large boundary faults, followed by another stage, a more advanced stage of internal faults. Internal faults, which are a system of faults which are oriented differently with respect to the large boundary faults. So we have these two different fault systems with different orientations. In this case, the internal faults, they form kind of segments, kind of an echelon segments you see here of areas of dense internal faults, which are somehow connected by a transfer zone, which is characterized by an oblique slip kinematic, so a component of transcurrent motion in between these two internal faults, which are orthogonal to the vector we have imposed to our models. And this is a very interesting result because this is very similar to what obtained in previous numerical models by Jolante van Beek. In these numerical models, at the end of the formation, we had something very similar. We have two segments, an echelon segments with maximum lithospheric thinning and also maximum magma production because of this this thinning and the increase, the compressional melting induced by this faster plate thinning and astenospheric upwelling. So we have a very good correspondence between analog models and previous numerical models. So these simple models, they just confirm the view suggested by Cindy and others during the 90s that we passing from the boundary fault activity in the southern med to the axial fault activity in the northern med is somehow related to an along axis variation in rift maturity, passing from the initial stages in the south to more advanced stages in the north. The question is, why do we have this significant along axis variation in rift architecture and maturity in such a somehow small distance in the main Ethiopian rift? And of course, we have many different parameters that can control the evolution of rifting, and so in principle, this along axis variation. We have parameters such as, or processes such as rift propagation or different crustal thickness, different velocity of extension, width of the deformed zone, and so on. What we found by means, again, of several different series of analog models is that obliquity and the different kinematics, the along axis variation in rift kinematics in the main Ethiopian rift can play a major role in controlling this variation, because, as I explained you at the beginning, the reactivation of this pre-existing weakness creates condition of orthogonal rifting in the south and oblique rifting in the north. And this has two main consequences. The first one is that if you pass from orthogonal rifting to oblique rifting, you change the dimension of the axial segments, because the higher is the obliquity of rifting, and the higher is the obliquity, and the smaller are the axial segments that can develop within the rift zone. And this is somehow what we see in Ethiopia, because passing from the southern part to the northern part, so from the less oblique to the more oblique sectors, we have a reduction in the dimension of axial segments. And you see here that in the northern part, you have very small segments because the obliquity is the highest in this sector. But the other very more important, probably more important consequence of obliquity is that rift kinematics has a strong control on the evolution of rift, in a sense that the higher the obliquity, the more rapidly the formation migrates from the margins of the rift to the axis of the rift. So this means that the higher the obliquity, the more rapidly rifting evolves. And this, in our view, can explain the variation in rift maturity passing from the southern Mediterranean rift, where rifting is orthogonal. So we have a slow migration from the margins to the axis, something that has not occurred yet in the southern part of the rift, to more advanced drifting, to axial faulting, because of a rapid migration in the more oblique sectors of the Mediterranean rift in the north. So obliquity can explain this along axis variation, and this has very important consequences also for plate thinning and volcanism, magmatism in the Mediterranean rift, because the rapid focusing of deformation at the rift axis resulting from oblique rifting in the north promotes a very efficient thinning of the lithosphere in these sectors of the rift, because the more localized is the formation and the more efficient is the thinning of the lithosphere. So the more efficient is the decompressional melting. And this, as also suggested by numerical models by Jolante van Beek, this may explain the increase in recent volcanic activity passing from the southern part of the rift to the more oblique northern parts of the main Ethiopian rift. And this has another important consequence on the evolution of rifting, because in the conditions of voluminous magma intrusion of the lithosphere, we have a significant thermomechanical weakening of the lithosphere at the rift axis. So we have injection of hot material, we have weakening of portions of the lithosphere interested by this intrusion at the rift axis. And this has shown by many analytical and numerical models by, for instance, Roger Bach in the past. This has an important effect on the resistance of the lithosphere and on the amount of forces required to rupture the lithosphere, because we have weakening of the lithosphere, which induce and promotes a self-reinforcing processes, because the more localized is the formation, the more efficient is steaming, the more efficient is magma production, but also the more efficient magma production and intrusion, and the more weakened is the lithosphere at the rift axis. So we have what we call the beginning of magma-assisted rifting. So a rifting which is significantly influenced and promoted by magma and magma weakening. And this is like when you put a piece of butter on a fire, butter melts and its resistance goes to zero. And this is somehow what happens to a lithospheric plate when subjected to significant magma intrusion and heating and weakening. So we are able to reach conditions of plate rupture very rapidly at these stages. So this is very important because, of course, since obliquity promotes a very faster, let's say, evolution of rifting, obliquity can be a key factor in promoting faster continental breakup, as suggested by other numerical, for instance, studies by Sasha Brun and this group. So obliquity is a very important parameter, or at least rift kinematics is a very important parameter in controlling rift architecture and evolution. So to summarize the story of rifting as shown by the many Ethiopian rift examples, we can go back to the influence of tectonic inheritance and rift kinematics on this process. And we can summarize, I mean, the influence of these two important parameters by saying again that inheritance and the pre-rift lithospheric structures has a strong control on the geometry of the formation, but also on the along axis variation in the architecture of rifting. So the alternation of symmetric versus asymmetric portion, especially during the initial phases of rifting, and also as a control on the along axis variation in rift kinematics, because the plan view geometry of this weakness in relation to the vector, the motion vector between the plates can control the transition from orthogonal to oblique rifting. And in turn, the variation in rift kinematics may explain the recent axial segmentation of rifting, but also the along axis variation in rift maturity, because the faster, the higher the obliquity, the faster is this migration from marginal deformation to axial deformation. So this suggests that the kinematics of rifting is probably one of the most important parameters in controlling the rifting process itself, because again, the higher the obliquity and the faster is the evolution of rifting and the progression to continental breakup. And in general, as we see during rift evolution, in these late stages of rifting, the tectonic inheritance has a lower influence with respect to the initial phases. So we have a decreasing influence of tectonic inheritance during rift evolution. Although we still see important influence of tectonic inheritance and the occurrence of the existing structures in at least some of the characteristics of rifting in Ethiopia. And for instance, we see that in some places like here, close in the central part of the rift, close to Lake Lagano, we have some atypical features in the architecture of the large boundary faults. For instance, we have this strange pattern of rhomboidal faults or zigzag fault patterns, which can be typically related to the occurrence of large pre-existing transversal structures in this area. So still a control of tectonic inheritance on the geometry and the characteristics of these large boundary faults. We have similar examples, for instance, in the southern part of the rift, where we have typical angular pattern of faults or zigzag geometry of faults, which still suggest control exerted by pre-existing basement fabric or in general inherited structures on the geometry of the large boundary faults. And we have many other examples of control of pre-existing structure on some of the features of the volcanotectonic features of rifting. For instance, we have the formation well away from the rift axis in the plateaus surrounding the rift, the so-called off-axis deformation or off-axis volcanism with, for instance, extension parallel faults, which are very atypical if considered in a homogeneous lithosphere, and this is normally related to the occurrence of what I showed you before, the existence of this large transversal pre-existing weak zone, which have controlled these characteristics of off-axis deformation. So again, the influence of tectonic inheritance decreases during rift evolution, but it is still observable in some features of the volcanotectonic, of the characteristics of the volcanotectonic activity in different parts of the main Ethiopian rift. And with this, I conclude, and I thank you very much for your attention.
Well, Giacomo, thank you very much for this very interesting talk and showing us that actually the MER segment is actually like 3 segments.
Yeah.
And and showing the importance of obliquity on the rift evolution. So now I'm going to ask everyone if they have a question. You can write something in the chat or unmute yourself and interact directly with Giacomo. Any question?
May I have a question?
Yeah, go ahead. Go ahead. Unmute yourself and ask your question.
After all, thank you very much to Giacomo Corti for this clear and interesting presentation. And I'm curious about if they have got new data about the distribution of seismicity in this area that can also support their hypothesis of rifting migration.
Thank you very much, Alberto. Nice to see you. Well, since the Eagle project at the beginning of 2000, there are many seismicity data collected in this area, and they support this kind of complex evolution with, mostly marginal seismicity, significant marginal seismicity with only subordinate at the rift margins and with subordinate seismicity in the central part of the Mediterranean rift, where transitioning into a more axial seismicity in the northern part of the rift. Of course, the picture is always not so clear, not always so clear, because we have seismicity related to volcanic complexes like the large calderas in the central part of the Mediterranean Rift, like Corbetti or other calderas. But the general picture of seismicity seems to support this view of a long axis variation from marginal deformation in the south to axial deformation in the north. And of course, there are still ongoing studies brought on by English people and others, but also here in Florence, Derek Keir and others, they are still collecting data on this.
Thank you very much.
Any other question? Okay, so I'll ask one. I was just curious about the inheritance that the mantle plume itself would have caused. Like, is there any evidence or...
On what? No, I didn't.
You talked about tectonic inheritance, but what about the weakening of the lithosphere by the mantle plume itself prior to rifting? Yeah,
I think it's a good point, and I think it has a very important influence on that. The interesting point is that if you look at the classic paper by Cindy Ebinger, what it suggests is that of course, this plume material is not homogeneously distributed at the base of the lithosphere, but tend to follow somehow the topography of the lithosphere, which is somehow inherited by past tectonic events. So probably the weakening induced by the plume adds to the weakening or reinforces the weakening related to the presence of this large scale heterogeneities in the lithosphere. So I think it is important, but it's somehow that reinforces the somehow rheological heterogeneity related to the existence of suture zones or Pan-African belts related anyway to past tectonic events. So it's something like that adds to this rheological inheritance. It is a thermomechanical weakening that, reinforces the process, I think, at a large scale, of course. Yeah, but you mean it reinforced, but it's not generating the. It's not. I think that the past tectonic events are probably at least one of the major factors controlling the existence of these weaknesses and this rheological heterogeneities. So it's not the plume itself that generates the weakness, but I think it's also a rheological characteristic related to previous tectonic events, like in this case, the collision between East and West Gondwana and the existence of a complex deformation zone in between. Yeah, sure. That's okay. Thank you very much. I think there is a hand raised.
Yeah, there is. Izeldin Yusuf, but I told him to unmute himself.
I don't know if he wants to ask a question. It was just.
Yeah, or there was. Or it's just a mistake.
I don't know.
I have no question in the chat. And,
yeah, I came back. Okay.
Okay.
Yeah, I came back to you. Yeah, just I want to thank Professor Corti for this very interesting and inspiring presentation. And I just have a small question or remark that you see, the Somali plate and the Ethiopian plateau or plate, they are separated by this Ethiopian rift. And there is a weakened zone in one of the diagrams. I have seen that there is a weakened zone between the Somali plate and the Ethiopian or African plate. This zone, is it a result of the rifting in this area, or is it a precursor to the rifting and it determines the location of this rift?
It is something that was there before rifting and conditions the rifting, so localizes the rifting and not the opposite. The reason why probably we had this kind of narrow rift in that area is that there is a weak zone there, and the weak zone localizes the formation.
So in this case, are there any field evidence, field or geophysical or geological evidence for this weakened zone that has determined the location of the super rift?
There are many there are geophysical evidences for this. Yeah, mostly based on geophysical evidence, and of course the different geophysical signature of the two lithospheric blocks at the sides of this area. Of course, it is difficult to say that it is actually weaker than the surroundings, but it is thinner than the Somalian and the Ethiopian blocks, especially the northern parts. And so probably it is, and also the distribution of the formation testifies that it is somehow weaker than the surrounding, especially the Somalian blocks. But anyway, there are evidences, geophysical evidences for this, and there is a classic Keranen and Klemperer paper 2008 clearly showing this, clearly suggesting this.
We have a question in the chat by Jean-Paul.
Okay, thank you very much, Professor Corti.
Sorry.
Thank you.
So we have a question in the chat by Jean-Paul Agumimana. So last year, Nyaragongo volcano erupted, and there were something like marginal deformation in Gizenyi city. May we call it rifting?
Well, normally this event are somehow related. I think that it is difficult to relate a single volcanic eruption in central volcanoes like Nyiragongo with actual faulting or marginal faulting in rift. It may be possible, of course, because the two processes are related. In the specific case, I don't know in detail, but in principle, it may be possible, but we need to find, of course, evidence, geophysical and geodetical seismicity evidences for relating these two processes.
Thank you very much. Okay, so last chance, everyone, for a question. Jean-Paul say thank you to your response.
Yeah, thank you.
No? Okay. So maybe we'll end it there. So I'm going to stop the recording.
Okay.
And I thank you again very much for your talk, Giacomo. It was really good.
Thank you too. Again, I repeat that this is a very nice and useful initiative. I really enjoyed watching some previous seminars by Cindy or Tanya Furma. It was they're normally very inspiring, very useful.
Well, we'll try to keep that going.
Okay. Thank you very much.